So, all right, to our guests today, we are very happy to welcome James Evans from the University of Chicago here, where he is a professor at the Department of Sociology. Among his very many duties he is, among others, the director of the Knowledge Lab at the Chicago University, focusing on analyzing science itself with large-scale computation. Also, he is a founding director of the Master Program in Computational Social Sciences at the University of Chicago. He has served as an associate editor at the American Journal of Sociology, and he is an external faculty member at Santa Fe Institute and Northwestern University. Currently, he's focusing a lot on the emerging field of science, where his most cited paper, Science of Science, from 2018 in Science Magazine is also about. And today, he will be talking about two very interesting preprints that are out right now. The first one on what he calls the L ratio, and the second one on academic aging. But before I take everything away, please, James, the floor is yours.
Thank you, friends. I always love coming to the Institute for Analytical Sociology, and so it's really a pleasure to be back. I'm excited to talk about some new work. These are some fresh ideas. They build on prior things that I've shared with those of you that I know and have seen in the past, but these are brand new pieces. One is going to come out in 2 weeks in PNAS, and the other's under review at another multidisciplinary journal. Here, let me share my screen. Can everybody see that?
Yes.
Yes.
All right, great. So yeah, today I'm going to talk about the social, biographical, and demographical locus of innovation in the context of science and technology development. And as was mentioned, I spend a lot of time trying to think about and to deploy, I would say, big data, machine learning, intelligent crowdsourcing to do, I would say, kind of a big data science studies to represent knowledge at large scales, to understand it, which is to say, to understand the distributions of heuristics, biases, and subtle institutions that shape how it is that we collectively think, reason, and know. And then to use those where possible to transform the scientific landscape in the scientific, scholarly, and civic process of really knowing more about how we know to improve that collective knowledge. And so we spend a lot of time measuring these things, these structures, these representations, these knowing states, from sensations to plans and action. And in particular, thinking about how it is that systems think. Here, I'm going to focus on how science as a system thinks and how it can think better. And so we've tried to really forward these questions. Here's the Science of Science piece, other pieces about meta-knowledge and about crowded frontiers to articulate to the scientific community the importance of using the full space of scientific imaginaries to study science and innovation. And why is that important? Well, it's important because science and technological innovation represent core driving expanders or growth engines of the economy. And it's also a critical humanity as we understand, define, and redefine who it is we are as human beings. But these are critical organs of societal growth, and really the basis of all modern credit, all modern promissory notes are that we're going to be able to do better, think faster and farther, be able to accomplish our purposes better as a function of new discoveries that we will make in the context of science and commerce. And so today, the two chapters that I'm going to focus on are one, how flock teams drive scientific innovation and confer more equitable productivity and credit across the groups that produce them. And the second is how aging limits the rate of scientific advance and slows the churn of ideas. I'm not sure how church of ideas got in there, but I guess there's some deeper spiritual, religious subtext that I myself hadn't accessed until this moment. So the first paper really builds on a prior work that I've talked about at IAS, for those of you who were here, that I'll mention really kind of in brief and summary, because it really formed the basis of that subsequent analysis. This was a paper in Nature about the ecology of research that really focused on how large overlapping teams dampened disruption in science and how small disconnected teams amplified it. And in particular, we were focusing on this really interesting measure that was put forward in the context of technological innovation by Russell Funk, Jason Owen Smith. And this paper focused on the degree to which new work and the stories that were told about that work in the future basically rendered that work in terms of an incremental advance based on prior work or as a new direction. So basically, did this new work, or to what degree did this work render this work in the context of its prior work, or see it as a new direction and render it that way? And it turns out that this purely structural measure has some interesting properties. If you look at it against words in the context of science, then it's negatively associated, and most strongly negatively associated, for example, with endorsing, confirming, and demonstrating in verbs, versus positive associations with change, introducing, and advance, right? So negatively associated with theory, model, and hypothesis, but positively associated with tool, device, and technique, negatively associated with across, within, and along, and positively associated with how, what, and why. And these aren't cherry-picked, these are like the margins or the extrema of the word distribution, of course, which was not selected on to develop this measure. And you can validate it in a number of ways, ranging from Nobel Prizes to kind of like extreme papers. In particular, it renders things that are of the same impact level in very different ways. So for example, these first two papers here that I have on the left, the Davis et al. Paper and the Bach et al. Paper. The Davis et al. Paper was really about the operationalization of a theoretical quantity that had been proposed 80 years prior, had been formalized, experimentally produced, and analyzed. That paper was an important paper, received many citations, including the Nobel Prize and other awards. But everything that cited that paper cited the work on which it had built 80 years before, these Bose-Einstein condensations that it formalized and well, that had been formalized and then it operationalized and constructed. Versus this Bach et al. Sand pile paper, which really kicked off the space of complexity research. It cited several things, but people recognized that paper as the beginning of a new direction. It synthesized them in ways that had not been done before and really kicked off a set of conversations that could not be traced to the work on which it built. And so you can render all papers and all knowledge contributions from purely the structure of stories that are told subsequently in this way. And when we analyze this in terms of large and small teams, which is the x-axis in these papers, we saw that disruption really almost exponentially drops as a function of team size. And that that citations grows in a much smaller increment as a function of team size, right? And so how is it that this is happening? We'll talk about in just a minute, but we saw across, this is true across, times, fields, topics, places, within authors. So author fixed effects, about 66% of the effect is within people who change between various team sizes and between impact levels. It doesn't really matter what a small team is. You can cut the distribution anywhere, and you can see significant differences, for example, between 28 and 29 team members across the population. And we accounted for very subtle, specific semantics of the field. One of the things that's striking about the citation implications is that basically large-scale teams end up focusing on yesterday's hits. And so they're building a way of ensuring their success as a function of building on things that already have eyeballs, right, yesterday. And so it's like a big movie production company. Are they going to decide between, some new independent script, a Slumdog Millionaire that hasn't been written yet, or Transformers 9? And the answer is Transformers 9, right? It's going to get the receipts of Transformers 8 minus epsilon, right? It's got a built-in market. And as a result, you see that the effects and the citations that these large-scale teams receive are much more quickly appreciated and then depreciate. And so one of the things that this left us with, well, to what degree is this about size? And to what degree is it really about the structure of the team, right? Is it just, I think there's size issues, and we show in this new work that size matters, but to what degree is it about the fact that small teams may, on average, be more like mesas in the landscape of scientific production, and large teams like pyramids, right? With those that are directing on the top and the muscles that are being garnered for the work down below. And so we were thinking, well, how do we calculate this ratio, right? This kind of brain to muscle ratio in the landscape of these teams. How much activities are concentrated within a single person or a few people versus across the team? And we have the advantage of this movement towards transparency and fairness in the context of scientific credit. So Nature and Science and PNAS and PLOS One and increasingly many other journals are now requiring these contribution statements, right? Like this, right? GZ, ZFC, and SDF conceived the idea and designed the experiments. GZ, ZFC, LY, and NH carried out the in situ STM experiments and analyzed the data. KS and MMF carried out the DFT and type binding calculation. MMA carried out the synthesis of the monomer. Text was initially composed by blah, 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 right? So who writes, who conceives, who engages in experimental exercise, who does those things exclusively or engages in them across the team. So you can recover from these descriptions what the activities are that are being performed. And when we cluster, right, the activities within person, so across all of these papers, across the contribution statements from their inception that are published by Science, Nature, PNAS, and PLOS One, about 90,000 such statements, we see really clean clusters, the optimal cluster using a kind of a silhouette measure, which is just basically maximizes the coherence within a cluster, and the separation between clusters is 3. You can also cluster it as 2, but the clustering solution looks like this. So lead, write, supervise, conceive, interpret, design, and coordinate cluster together, as do generate, conduct, develop, analyze, purify, prepare, assist, carry, transform. Very physical activities, really, on the left, which we call direct support, in support of this lead activity, which is defined by the word lead. And if you do a two cluster solution, you get the separation of lead and all these support activities. If you do the optimal in terms of separation as well as coherence, then you get a third cluster, which looks very much like very indirect support. Commenting, editing, providing, discussing, quote unquote, contributing. If I was being crass, I would separate these into brains, muscles, and fat, but they all play critical roles in the context of this team. So forgive this. So again, this is across the 90,000 papers for which we have these distinct activities self-labeled and self-described by the teams. And I should say that these descriptions are increasingly templated, which is to say the roles are templated or described. So for example, the credit, which is an acronym process, describes various roles that you should try to include if they're present in the context of your description. So the second step in trying to analyze the universe of scientific activity in terms of its group structure was to extrapolate these team roles from the 4 papers that we initially developed to the universe of scholarship. And how could we do that? Well, we looked at the relationship between these structures and the properties of and roles of individuals within the focal paper and within science as a whole. And it turns out there are really strong associations which are highly self-describing, right? So for example, to what degree does the author in a paper bring references from their prior corpus of authored papers to this paper, right? So to the degree that they do that, it strongly implicates the likelihood that they will be in the lead cluster, which is to say, leading, coordinating, designing, quote unquote, writing these papers. To the degree that they bring topics from their prior papers into this paper, they will be attributed as a leader, director, guide, etc. in this paper. To the degree that they are a leading author on the paper, right? The lead author or a co-lead author on the paper, then it's much more likely that they'll be ascribed this leading role, and the degree to which they're a corresponding author. So this is the role within the current paper with respect to the past. But if you look at their role in science, we also have additional signals. So if they're older in the scientific space, and the birth and the age year is from first paper, right? So to what degree are they participating in public science? To what degree do they have more citations? Attributes the likelihood that they're going to, or indicates the likelihood that they're going to be a lead author, quote unquote, or play that lead role. The degree to which they're engaged in topic diversity over the course of their careers is going to increase the likelihood that they're a lead author, and the productivity rate, just the number of papers that they're engaged in. So we basically can kind of take the distribution of those activities, identify the likelihood of lead and support, develop basically a linear or in this case, nonlinear separator. We could develop a linear separator, but we develop a neural network to kind of maximize this slice and are able to capture more than 80% of the variance associated with these things within the 90,000 papers and then extrapolate it to the universe of relevant scholarship. So more than 16 million papers. And then this is what we're analyzing in the context of how it is that different structures controlling for size and other features of the work itself influences the outcomes that follow, their implications for science as a whole. So first, what's the relationship between team size and team structure? Well, you can see in the top figure here, the percentage likelihood of leading direct support and indirect support over the course of a paper as a function of team size, right? And so we see the greatest likelihood, or the greatest likelihood of a team ratio, a lead ratio, which is the number of people with these lead appellations inside this description versus the paper over the number of people in the paper as a whole. This lead ratio ends up being maximized at 2 and then drops precipitously thereafter, really exponentially up to 10, and then kind of stabilizes thereafter at about 0.1. Right, which means, right, the average lead ratio is at 10, you know, one person, right, and they're on collapsing thereafter. Direct support maximizes at about 11, and indirect support maximizes at 25, right, and then you can see that that basically here's the L ratios that correspond with each of these team sizes, with M is the team size. So M equals 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And while, of course, you know, there's variation on both sides, there's really sizable variation even within those team sizes, right? Even within a team of size 10, you do have, you know, 1/10 of those papers which end up having a high L ratio, right? And the same with all these others. So there's a lot of variation there that really allows us to explore the degree to which team structure and not team size are driving some of the effects that we looked at before and more, right? So we're interested both in understanding the structure of credit, appreciation, and productivity for all the members of the team, as well as the degree to which these things contribute to science in the present and science in the future. So that's what we're going to explore. The first thing we find is the team structure matters for innovation in the scientific landscape and the scientific frontier. So we analyze this in 2 ways. One, with that same disruptive measure that we looked at before. And so we see, and so, developmental is just the flip side. It's 1 minus the disruption measure. So this is the degree to which a piece is seen as something new in the landscape. So the degree to which the paper that's produced by a team with a higher or lower L ratio, a story is told in the future that suggests that this is a new direction for science. And the second is novel combinatorial activity, the degree to which it's basically pulling together topics inside the paper in such a way that it's changing the landscape of science. It's bringing together things that are not typically brought together and change that landscape for the future. Now, in the past, this was done by looking at, so Brian Utsi and colleagues in a 2013 science paper looked at this in the context of the sources of a paper. And we're really interested in the degree to which it's combining ideas directly, and there's reasons to believe, which I won't, we'll choose not to talk about here, but I'm happy to take it in the question, that basically those journals are not a great proxy for the ideas themselves. So we take basically the topics. So we could look at the Z-score of the likelihood of their combination or recombination. It turns out in the modern world of representations that you can develop a really tight representation of that score by taking a neural representation. So basically, if you build an embedding which captures the position of those things in the content space, like the space of papers versus the context space. If you take basically the in and the output embedding, the inner product of those two things, pairwise across the space of keywords, then you're able to predict more than about 75% of the variance of the Z-score. And the desirable preference of this is that you're able to develop a dynamic measure, right? So if something is really successful, then it brings together novel components which become much less novel over time, right? Because everybody comes to appreciate the entire field reorganizes around itself. And so it's like my kids, when I showed them Star Wars for the first time, they're like, that's so boring. It's so utterly obvious, like what are these, tired tropes, that they're rendering. And it's like, well, yeah, it's tired, obvious, and out of date because it won, it dominated the cultural landscape. Everything else is copying it. And so, and incrementally improving on it. And so, so basically the benefit of this embedding measure is it allows us to turn the novelty measure into something that's equivalent to the disruption measure in terms of its relative change over time, right? So we're able to look at the degree to which something continues to surprise, right? Or surprises once, effectively changes the landscape and no longer continues to surprise. And what we see when we analyze these things is that when we have a higher L ratio, that there are much higher, almost 20% greater novelty across the space, which is almost linear across the space, and 167% less disruption, right? So, so dramatic changes in the degree to which these papers are accorded a changed direction. This relates to that finding that we showed earlier, that they're building on big successes from the past, right? The very recent past. And so, you're incrementally borrowing those eyeballs. It ensures you against irrelevance in the present, but it ensures also that you will be irrelevant to the distant future insofar as science changes. So this is really its impact. And I should say, these effects that I'm describing are, they're fixed effects within author, and we also do another fixed effects within field, right? In all of them, we're controlling for team size. The structure is a much larger effect than the team size. We're also controlling for the mean standard deviation and maximum of career ages across the team, the support from funding agencies, the number and the amount of awards from those funding agencies, and many other things. Now, when we look at their impact for scientists themselves, we find that team structure really matters for credit. So if you have a hierarchical team, then it's really good for lead author productivity. So the lead authors do amazingly well. But it's not great for the productivity of the support authors. Support author productivity is substantially increased as a function of their ability to participate in a lead ratio on this paper across other papers. And to be clear, it's not the lead ratio is that everybody is a brain and there are no muscles. It's that everybody's contributing as a brain or designer to the paper. They may also be engaged in the muscular activities of experiment, observation, and analysis. So it really matters for credit. And we'll see that this has a compounding effect when we look at the distribution of lead ratios and the author age distribution over time, which, I'll just, kind of let the cat out of the bag that basically lead ratios have been decreasing sizably and substantially since mid-century. And the aging of scientists has increased. And so as a result of these two factors, we have decreasing credit going to new scientists entering this space. And then finally, team structure really matters for the future, right? So if you look at the long-term citation impact, it's much higher. And you can see this real pop at about 0.75 to 0.8 lead ratios really pop for long-term impact. The likelihood that a paper, so this is its citation count after 10 years, right? Versus between 0 to 10 years, right? So as the higher, as L ratios go up, there's less short-term impact, a decrease of 121%, but sizably and substantially a pop in longer-term impact, right, by these small papers. So, and longer-term impact it's harder to justify, it's harder to bank on, and it doesn't provide a strong return in terms of grant dollars and appreciation at the moment, right? And so this is one of the reasons why we see large teams versus small teams have this respect. But again, this is, holding, again, constant team size, mean standard deviation, max career age, funding support, et cetera. So what are the implications of this? Well, we see it manifest in other places in the context of really substantial scientists. So the L ratio predicts Nobel Prizes with about 80% accuracy, which is actually, interestingly, very distinct from predictions of collective credit allocation. So there's a collective credit allocation measure, which was published in PNAS and shows this idea that if people cite a person's work with other of their work, then they give more and more credit of the original work to the people whose continuing work they cite, which is to say the Nobel Prize winners and others are not those just that contributed to sizable and important articles, but they also stay in the game, right? By staying in the game and by kind of connecting their future work with that prior work, they're effectively rebranding the prior work as theirs. And so that measure, also predicts about 80% of the likelihood of Nobel Prizes, but much more recent relative to Nobel Prize. This measure is calculated at the moment that the paper is published, right? The moment that not even the paper is published, the moment it comes out in the archive, the moment there's a description statement. So this could be 20 or 30 years before the Nobel Prize is actually granted. We can predict as a function of the likelihood that someone is a lead on that paper, they're going to be accorded the Nobel Prize. And Nobel laureates are almost 50% more likely to begin their careers working in flat teams with L ratios of greater than 0.5 and to be leaders accorded on those teams for their first publications, suggesting this potential new mechanism through which early mentorship experiences influences late career success. Flat teams on which young scientists participate not only act for their mentors, but they think with their mentors in the context of that work. Now, of course, instrumentally, it's difficult to know whether or not they were just genius scientists that forced their way into the lead ratio, or they were accorded the opportunity to participate as leads in that ratio. But the consequences are really sizable and stark when we think about science as a whole. So over historical time, junior scholars are increasingly likely to be involved in taller, like lower L ratio teams. The fraction of tall teams with an L ratio below 5 increases by 20%, from 50% to 70% over the last 5 decades, which it, again, has enhanced the productivity for those in the top, decreased it for those in the bottom. And the shift in credit allocation strongly favors senior researchers who have accumulated more publications over their careers, exacerbating the unequal distribution of credit for junior scholars. And that's a lead into this second focus on paper in this study. So this biographical and demographical locus of innovation project, where we're really interested in how it is that aging shapes the scientific landscape in terms of the character of science itself. There have been a number of scholars in the past who have looked at how scientific age changes in terms of Nobel Prizes, first grants, and others across the historical context of science. So, for example, this, I would say, really interesting and path-breaking paper by Ben Jones, The Burden of Knowledge and the Death of the Renaissance Man, is an innovation getting harder. He looks at the trend at first innovation, the age at first innovation, and the trends in age of the average innovators per patent, and is really able to show across the space of scientists that basically scientists are getting older when they get their first grant. Nobel Prize winners are older when they receive the Nobel Prize and when they did the work that is accorded their Nobel Prize. That basically, individual ages have increased when we think of kind of new to the world inventions. There's also Max Planck's intuition, where he claims that a new scientific truth is usually not propagated in such a way that opponents become convinced and discard their previous views. No, the adversaries eventually die off and the upcoming generation is familiarized anew with the truth. This, of course, is the basis for Thomas Kuhn's work, in which he really argued that displacement of certain ideas with other ideas, rather than the ability or the complete domination of new theories over all facts, but the domination of new facts or new theories over new facts, ends up being important as a function of the aging of persons and the familiarity of those persons with those facts. This formalism was articulated well and analyzed in the context of this really interesting paper, Does Science Advance One Funeral at a Time, by Pierre Azoulay, Christian Foss-Rosen, and Josh Graf-Ziven. In this paper, they took a sample of nearly 500 biomedical scientists. Biomedical science is the only place in which you could do this study. It's the only space that's large enough. These 500 scientists were star scientists within their subfields, and they defined their subfields as a function of the overlapping thicket of mesh codes, right? So these are medical subject headings. They identified these mesh code defined fields, right, independent of individual author paper construction, but of course the mesh codes occur across papers, which is how they defined these subfields. They find nearly 500 people who, in the scientific space, who are stars within these subfields and experience a premature death. Okay, that premature death could be completely unexpected, from like a car crash as someone's crossing the street, or largely unexpected, so very aggressive cancer, right, stomach cancer, for example, or a more progressive form of cancer that doesn't accelerate quite so quickly. So you've got a few years before the person dies. So they've got about 500 people within the space of unexpected deaths. And what they find is that subfield growth and innovation within the subfield is strongly positively associated with these deaths, right? So subfield growth. So these figures here are the years, the time to death, -10 to +10. And so you see this kind of like, for all authors, this increase in attention, productivity, papers, novel authors entering the space. The attention to collaborators of the star scientists, of course, go down, and those that are non-collaborators go up substantially. So what's going on is basically a soft form of gatekeeping, where senior scientists either directly, and they show this as a function of the likelihood that those authors and their students control editorial boards of journals and and grant disbursement agencies. So, for example, if they're on the NIH panels that determine the likelihood of grants, then that decreases the ability or the likelihood that this switch occurs, right? Because the continuing legacy of those star scientists is enforced. But when it's not the case, it's even more the opposite, right? And so the idea is either these star scientists, as a function of their early success, are actively policing and keeping out new individuals with new ideas, or those people with new ideas know that it's unlikely for them to gain traction in the context of that new field, and they wait, right, until there's an opportunity. So this is what we're interested in exploring at scale, and just trying to understand the degree to which science and aging really influences the character of scientific activity. And we want to scale that up to the populations of more realistic fields to understand its implication across science. So just an example, a story. As a 26-year-old patent examiner in the office at Bern, Switzerland, Einstein writes 4 papers that really revolutionized science's understanding of space, time, mass, and energy, right? So this is 1905. In the decade that follows, he enters the academy, generalizes special relativity, general relativity, but then from mid-career on, he seeks unsuccessfully to assemble core physics into a unified field theory, spends his later years almost exclusively criticizing quantum mechanics' probabilistic interpretation of the universe, posing quantum paradoxes until the end, 1955, some of which are observed, which ironically and against his wishes and fantasies entrench the quantum age. Right. And so the question is, was the young Einstein unique in promoting new areas with minimal reference to competitors? And was the old Einstein unique in defending past work against emerging ideas inconsistent with or irrelevant to it? Right. So this is really the question that we're asking. And then conditional on the answer to that question, what are the implications of the demographic shape of different fields for science and innovation as a whole? And our intuition, our theory is to the left here, really, is that science advances in time and that scientists age somewhat slower than their first and best ideas, right? And so you have this kind of popularity rank of ideas. To the left, there's no data. This is a cartoon. We've got ideas that like they're birthed at the frontier of science. And then, from this point of popularity and prosperity, they kind of, they like fall off gradually. And scientists have, if they persist in the space, a few waves, so they jump from their best ideas to the next space of ideas to the next space of ideas, each of them kind of falling in the space of ranks. And this is what we see on average as a whole when we look at individual scientists. So these are specific physicists that are studying thin film superconductivity, crystal scattering electron, and we see them kind of jumping, some of them don't jump. So ABS, publishes a couple of papers just specifically on scattering. But we see JDT jumping from superconductivity to an electron focus. And we see on average across the entire space of scientists, an aging of their references, which corresponds to a little faster than 1 month per year, right? So, and so you see to the left, this is kind of years from first publication that we see across the scientific age range, which is to say scientists who live actively published for 5 years or less, for 5 to 10, for 10 to 15, 15 to 20, 30 or more, and all across the entire space. We see that for scientists that only really actively live in this space up to 20 years, their favorite paper, which is to say the paper that they cite the most across their career, is the paper that came out the year before they began publishing. Right? So the ideas that were new to them at the frontier, right, are still new to them at the end of their career, right? So those fresh ideas, like that's that huge bump you can see for everybody. It's just before birth. For those who stick around for 30 or more years, their favorite paper was the first paper they published. Right, and they do extend the distribution of their attention, right? I mean, they survive, so they continue to, they do some learning, but they're moving away from that frontier actively. And so we see for all scholars this real linear increase in the average age of citation, and that increases, the slope of that line increases pretty dramatically as a function of early bloomers, early successes. They age much faster because their first paper is their favorite paper. Everybody else, their first paper is the paper that they read in grad school that just came out, right? That's you know, and again, these aren't cartoons. This is everybody. This is everybody in every period of science at all impact levels, at all continuities. It varies somewhat by fields, but not dramatically. And unsurprisingly, right, the field that ages the fastest is the field whose methods effectively have not changed for the last 200 years, right? So mathematics, there is no reason that a mathematician needs to update their impressions of a favorite paper that came out the last year before they published their first paper, right? Because the methods, that paper is just as true today as it was then. It's just as interesting. It's just as valid. And the field that has the lowest slope, ironically, is the field of effectively discrete math, computer science, whose methods are changing the fastest over this period. For everybody else, we've got an epistemic churn that keeps the disciplines effectively that growth, right? They can't complete, you can't hang your hat on findings that were built on methods in most fields 50 or 100 years ago, right? Because the epistemic standards have changed, and so you need to update faster. If we look at this in terms of keywords, so just the words that you're using in your paper. In this particular case, we use the Microsoft Academic Graph keywords, which is like a space of 2 million keywords that really are, I would say, a light normalization of the total vocabulary involved in the construction of these sentences, that we see dramatic increases in the repetition of keywords across your papers over the career age. Right, so from first to second to third paper, that stabilizes at about year 15, and a dramatic falling off of the popular keyword coverage from the frontier. So basically, from when you are minted, the first paper that you publish, we're normalizing this, right, from that first paper across these career ages, but you're dropping again exponentially from that frontier. So this is, you can think of the empirical inverse of the right figure here, right? But for all people, all papers, all fields, right? And so people are kind of like falling in that distribution, that rank distribution from the frontier. And it turns out that this aggregates in ways that are powerful. Right, so you see this negative association here in the slope between the churn rate of ideas within the field and the proportion of older scientists within that field. So here we do a discrete cutoff, but it doesn't matter. I mean, you can measure this any way you want to. You can't avoid this negative, almost 0.5, 0.41 slope in the association between the old proportion and the churn rate, and we'll look at that in predictive context in just a few minutes. So we also see something else that's very interesting. I would say this was the part of the paper that was, so everything else could be attributed to a passive change in the way that older scientists view new science. They're just less interested in new science than they are in old science, and the science that really, it's like, I grew up, my high school was in the 1980s, and I love 1980s music. I don't like it, like aesthetically, I don't like it, but there's something about those songs that were played during the prom, at that period of hormone peak, like there's something about that moment in developmental pathway that makes those, I vibrate in a different way to those songs than I do to songs that I much prefer from the present moment. And so that's kind of like a passive change. We're also interested in the degree to which there's an active policing of the scientific frontier by older scientists. And we're really interested in this work by the Allen Institute for Artificial Intelligence's team, Armin Cohen, Walid Amar, Madeline Van Zulen, and Field Katie, which published this paper on structural scaffolds for citation intent classification in scientific publications. So they build this relatively intense and highly predictive neural model that captures the degree to which, or is able to reproduce the judgment about whether a paper, when cited in a publication, is being criticized or contrasted with the current work versus being used in a supportive capacity. Like we're building on this prior work versus, as opposed to this person, right? Or we criticize the work directly of this person in developing a foundation for this current work. And so what we see is this acceleration of criticism in people's paper construction over the course of the career. And that criticism is primarily to young papers. And the reason it's primarily to run young papers is because most people who are publishing papers are young, right? So most people stop publishing after their first paper or their second paper. Most people leave the system. So what we see is this really sizable increase in the likelihood of criticism rate, this contrasting claim probability rate over the course of the career, which eventually has diminishing marginal effect over the course of that career. And you can see it's distributionally focused from older to younger. This is the second. This is basically the delta of age between the paper that's citing and the paper that they contrastingly cite, right? So you see the density, the dramatic weight of density is older papers criticizing younger papers, much more likely than the converse. Any paper that you see coming out that ends up gaining substantial cites, you see basically a bifurcation in supportive versus contrastive cites. So the Higgs boson paper to the left, this is a cartoon of this, but we've done hundreds of these, not to illustrate the point, just to investigate and kind of push the point. The Higgs boson paper. So if the authors are older from that paper, they're disproportionately critical of the paper. I mean, you can look at the two densities there, and this is not cherry picked. I mean, this is one of several. The first one we did was actually the Brian Utsi paper about using the z-score associated with the unlikelihood of citation sources. Those that cited it that were critical to it, they were all older. Those that cited that were supportive were virtually all younger, with a distribution that was even starker than this. So basically, in short, scientists are like, on average, the older Einstein. So they're not just promoting and interested in their early work. They're not just passively ignoring the present. They're actively policing the field. That is increasingly what they do. That characterizes their scientific activity. So then the question became to us, what's the impact of this when we think of this as a demographic system, right? So fields themselves are aging. There's an individual effect. There's a kind of a life course effect, but of course people live inside teams and they live inside fields, and we're treating them as individual and autonomous agents. And so what we see is, yes, it's true that teams that are heavy in the size of their fields are less likely to age as fast. And the reason is, of course, on average, that older scientists are tied with younger scientists, and we'll show what that effect looks like in a few minutes. But here we're interested in what the relationship is between individual scientists and the mean age of the fields that they're studying. We use the same definition of these overlapping mesh fields, but again, it doesn't matter what definition of field you use, whether it's a coarse, large-scale field or it's a small-scale field. We find the same effect, which is that there retains a very strong individual scientist age component. So this is reference age by the average career age right across the field. And what you see is that there's also, or remains, a significant, statistically significant, not as substantial, but marked positive effect of mean age of the field. So you have a slope for your average age effect, which is accelerated, right, in an additive fashion with the team. So, and this is holding constant mean age within field, mean team size, individual team size, right? All these other structural effects, which, some of which also impact that likelihood. And so what we see is that, if you have an older proportion, then there's just a higher proportion of criticism for younger work in those, there's a higher preference for earlier reference ages in those fields. We find that the effect is slightly different for the criticism rate. That's why I caught myself there. There's still a strong positive effect of scientific age controlling for, again, individual team size, average team size of the field, a number of other features in the context of this space. But then the criticism rate goes up strongly as a function of scientist age. It goes down slightly as a function of mean age because there are so few young ideas to criticize, right? So as you have fields that are increasingly old, there's just not, they lock down, they become crystals in ways that I'll show in just a minute. So we were interested in the relationship between the old proportion within those fields and the churn rate. So the likelihood of replacement of ideas within those fields. Because you can imagine the causality going in both directions, right? It could be that the fields age, and so people are increasingly defending their epistemic prior commitments, and they're shooting young ideas, and that slows down the churn rate. They can't get published, they can't get grant funded, and they really can't advance or disrupt the field. You can imagine it going the other way, right? That the churn rate slows because a field runs out of steam. The ideas required to explain the phenomena are not forthcoming, or they've finished, and young people just not entering the field. It's a bad bet. And when we do Granger causality estimates, then we see that the old proportion predicts the churn rate much, much more strongly and consistently than the churn rate predicts the old proportion, right, across these fields. And even in the fields where we see a double effect, when it looks like it's going in both directions, then the effect for old proportion on churn rate of the future, again, this is prior old proportion decreasing the churn rate in future years versus prior churn rate decreasing old proportion in future years, regardless of the lag, comes in favor of old proportion, basically decreasing churn over churn decreasing old proportion. Now, are we hopeless? There are ways that you can grow young, that your citation and attention can update. One has to do with this team size effect. You can basically drink the young blood of your collaborators. You can collaborate with young people, and the degree to which you do that decreases the rate of aging, and does so relatively dramatically. The second is, I have the Stay Hungry, Stay Foolish page at the end of the Whole Earth catalog, right? So the degree to which you're a rolling stone and move from institution to institution changes your view on the world, the character with which you analyze your work, and decreases that rate of advance in age. And the degree to which you just change fields entirely, right? The degree, which is to say, the degree to which you change who you are, right, as a scientist or scholar, that decreases that rate, not as substantially as collaborating with young people, but also substantially. So really the conclusion here is that, we really, in pulling these two ideas together, we're activating diversity to catalyze advance. And when we deactivate diversity in ways that I'll describe in just a minute, then we really slow advance. So innovation in science and culture, I'm arguing, is fundamentally high dimensional. Which is to say the fitness landscape is high dimensional, that it's a complex space There are lots of local maxima that we get stuck on, and it requires diversity to understand that that rich space. It's not like hill climbing on some smooth developmental landscape. This requires novel combinations of people, techniques, and problems. And I'm trying to show here that population and team structure are critical to activating the diverse intelligences which are present within the space of a team and within the space of a discipline. That hierarchical teams in particular are constrained by the ratio of brains at the top, which are directing, conceiving, imagining, and framing the research. And the aging scientists are constrained by brains in the past, right, by their own prior commitments and understanding of the landscape of future work. And of course, this work was not done alone. The first flat team paper is first authored by Feng-Li Xu, who's a really wonderful postdoc in my lab now, and Lingfei Wu, who was a former postdoc and is now at the University of Pittsburgh. And the aging paper is first authored by Haochuan Cui, who's a visiting student from Beijing Normal University and also co-authored by Lingfei Wu. So with that, I'll stop and open it up for questions. Love your thoughts and ideas about this work.
Yeah, thank you very much for this super interesting talk. I think there was a lot in there, and we can start with the Q&A. I'm gonna stop recording now, so please raise your hands.